So we'll continue our quantification of circular motion by analyzing or talking about Newton's second law applied for circular motion. And so we can start with just Newton's second law in general. The acceleration of an object is the net force divided by the mass. And the only thing that changes is this right here, the acceleration. So for circular motion, we get the centripetal acceleration. The centripetal acceleration would be the net force centripetal divided by the mass. So this is the net force centripetally. And then we can also think about the acceleration in the y direction. It would be the net force in the y direction. I'll talk about the difference between these two divided by the mass. So this is similar. This is a component form. So we have a centripetal and a y. What this comes down, let's think of an example. Suppose we had a car traveling around a turn. So it's going around a circle, a curve like that. I know it's not a circle, but it's close enough. So this car is going around it. What we have is we have two components here. We have one acting centripetally or radially towards the center. But then if you look at this from behind, what we would see is the car kind of like this. So we're looking from behind the car. So the car is driving into the screen and it's kind of doing the turn like that. So we have a force centripetally this way, but then you also have these y components. So something going on in the y, and then you have like the force of gravity. And so sometimes we have to analyze both these components and these components to figure out what's going on. So it's similar to x and y, except now we'll do centripetal or radial and y. Working through some examples, you'll see how this all works out. And then knowing that this part right here is v squared over r. And that would be your net force. And then you can rearrange this thing, your net centripetal force divided by mass. And then we can multiply and solve and do whatever we do. All right, let's do an example. So Josh drives his car at constant 12 meters per second over a bridge whose shape is bowed in a vertical arc of a circle. Okay, so we're gonna have this bridge that kind of looks like a circle. It's a crazy bridge. Okay, and so he's going over this thing, the direction and magnitude of the force exerted by the car seat as he passes the top. Okay, so it's gonna be up here. Just drawing a little picture to make sense of it. The radius is 30. So let's go ahead and do that. So we have a 30-meter radius. He's traveling at 12 meters per second. That's tangential velocity. Kind of going this way. And his mass is 60. We'll come back to that one. The key is right here. What's the force of the car seat? So I'm going to pull him out. So he's in the car. And so what we want to know is what's that force pushing him up? And the force pushing him up would be the normal force of the seat. That would be the force pushing him up. All right, so let's pull out a force diagram for this. So we're going to make Josh our object. So in this case, we have the normal force of the seat pushing up. This would be the normal. Now, since he's turning this way, we know that the acceleration, the centripetal acceleration, always points towards the center. And we also know that the net centripetal force has to go in the same direction. So we know that these are all radial components. So we know that the force of gravity has to be straight down, which is going to be in this direction, and the net has to be bigger. Therefore, the force of gravity must be bigger than the normal force. So I'm going to draw it bigger. That would be the force of gravity. Okay, so remember that this quantity is mg. So this doesn't change. It doesn't matter where he is. if he's at the top or the bottom. This quantity will be the same. It's this one that has to change in order to give us a net force down. Remember that he's going over a circle. Okay, so now we can use Newton's second law, which says that the centripetal acceleration is equal to the net force centripetally over the mass. I'm going to move the mass over there. So you get mass times the centripetal acceleration is equal to the net centripetal force. So what we're going to do is we're going to add up all the forces that are acting centripetally, either towards the center or away from the center. And what we'll do is we'll call towards the center positive. So we're going to call this positive. So we get mass times, I'm going to go ahead and change the centripetal acceleration because I have velocity and radius. So this would be v squared over r is equal to the net force. Since down is positive, the normal here is going to be negative. So we would get the negative normal force and then plus mg. Okay, we're trying to find the normal. That's what we want. That's our target variable. So we can solve for that. And what I'm going to do is I'm going to move the n over. So I get the normal force is equal to this part, the force of gravity, minus this stuff, minus mv squared over r. All right, so the normal force is going to be the mass, which is 60, times 9.8, minus 60, times the velocity, which was 12 squared, divided by the radius, 30. So what you can see is that this is his weight. So if he were just standing still, the normal would be equal to the weight, but we're actually subtracting away from it. So if you calculate that thing, let me calculate it. You get that the normal force is equal to 300 newtons. Okay, so let's make sense of this. This is what we always do. So sitting still, the normal force, so if he's just sitting there, let me just draw him. So not moving. Then we know that the normal force is equal to the force of gravity. And the force of gravity would be 60 times, so that'd be like 600, approximately 600 newtons. So the normal force would be 600 newtons. But when he goes flying over this arc, we see that it's only half of that. So what does that feel like? Well, if you're sitting in a car and it goes over a hump, you feel a little bit weightless. You feel like you're coming out of your seat, and this is why. Because the normal force has been reduced. Conversely, when you go through a dip, what do you think is going to happen? How do you feel? Well, you feel a lot heavier. And the reason for that is because you have to have an acceleration upward, so your net force has to be up. So the normal force has to be bigger than the force of gravity in order to give you that acceleration up, so you feel really heavy. We kind of did that with the pilot. All right, let's do another example. Okay, now we're going to look at a rotor ride. It's kind of like the roundup. Anyway, a woman's in it. The drum spins around. So let me draw a picture of what's happening. So you kind of have this big drum-like thing. Big cylinder. Should have drawn this before. Okay, and then what happens is you stand against the wall. So you're just standing there. And then this thing starts spinning around. So it spins around like this. And then once it gets up to speed, the entire floor drops. So the floor drops down like this. And then you're stuck to the wall. You know what? Let me find a video. Show you what it looks like. All right, so I found this video. So you can see all the people, they're kind of standing against the wall, and it starts speeding up, and eventually you'll see the floor should drop down, and then they'll all be stuck against the wall. Let me fast forward a little bit. There it goes. It's about right there. Okay, there goes the floor. So you see everybody's stuck up on the wall. Pretty fun, huh? These people are, that's typically what I did. And I'd always put my feet up, so you look all cool. Those guys. Anyway, that's the rotor ride. Okay, so what's happening here? So let's try to explain what's happening. What we'll do is we'll take one of these, we're going to take this person out, the woman, and we're going to imagine her in we're going to look at the Y and radial forces or centripetal forces. So when she's standing there, there's a force pushing her in, that's off the wall. So we have this force coming in, and that's actually the normal force from the wall. That's the normal force of the wall. And then of course you have gravity pulling down. So you have the force of gravity. And then what's holding her up? Well, it's going to be some friction holding her up. So you're going to have some, since she's not moving up or down, that's static friction. So these are our forces that are going on. And this force, the frictional force, remember, is dependent on this force here. And so we're going to have to move from the centripetal and the Y and so on. So let's think about, remember, this is our Y and our radial or centripetal. So the net force in the Y direction is 0 in this case. She's not moving up and down. So what we can see is that the friction force is equal to the force of gravity. And then the friction force, to calculate that, that is I don't even know if we need to move into it, because that would be the coefficient times the normal. We can figure that out. So let's see, the coefficient of static friction times the normal force is equal to mg. Okay, but the normal force is centripetal. So now we need to go over to centripetal. So the acceleration centripetally is the net force centripetal over the mass. So we get mass times centripetal acceleration is equal to the net centripetal force. And the normal is the only force acting centripetally. So now we have mass times centripetal acceleration. Well, they don't give us velocity, they give us period. And we know that the centripetal acceleration is equal to 4 pi squared r over t. That comes from the definition of period, which is 2 pi r, the circumference, divided by the velocity. And then we just took this and put this in for v squared, and that's where this comes from. So that goes into that. Okay, so that's our normal force. So now I can take this quantity and we're going to plug it in back over here. So we get the coefficient of static friction times the normal, but the normal is m times AC is equal to mg. So notice mass is gone. So for this ride, the mass of the people didn't matter. You saw everyone that was in there was stuck. It didn't matter if they were big or small. So we get the coefficient of static friction times the centripetal acceleration. I'm going to go ahead and substitute this here now. So we get 4 pi squared times r divided by t equals g. At this point, we can plug in some numbers, and so we can, we can explain. So it's basically, let's break this out. So we get r over t. I'm just pulling out this little fraction because these are all going to be constant, times coefficient of static times 4 pi squared equals g. So we can see that it's just going to be a ratio of the radius and the period, and we can plug stuff in, and that's what's happening. Anyway, the faster you go, or the less the period is, the greater the acceleration. So the greater the normal force will get, creating more and more friction. But you just need to get the normal force such that the friction force is equal to the force of gravity. And that's the rotor ride. So now let's do one with cars so that you can understand what's happening with cars going around turns. Actually, I'm going to stop there. I think we'll do the cars in class. Or I'll make another video specifically about cars going around turns. That's it for now.